hope you're back, and now you will fall asleep. And I will not allow you because I will be quite provocative, I hope so. When we come to energy planning, the first question is which tool to use? And there are a lot of them. This is a very nice review paper that shows 200 different energy planning tools that can be used. And they have very different optimal points, very different positions what they want to solve. So you have to actually understand what is your problem and how best to solve that problem. There are basically two major sides of energy planning. One is energy demand, and the other is energy supply. We talked a lot today about energy supply, but what about energy demand? Basically, the old way of planning the demand is wrong because we are changing technologies. In times when technologies are quickly changing, you cannot use econometric approach. It doesn't work. It will never see that your demand is actually falling where your GDP is growing. And this is what is happening now because of energy efficiency of buildings, transport, industry also. So in order to properly model energy demand, you have to go not to the final energy use, because that will give you completely wrong result. You have to go to useful energy use. And what is useful energy use for a building? It's the envelope, or it's the floor area. It's not the energy used in buildings, because that one is something we want to change significantly for 5 times in a long period of time. So in order to properly model demand, you have to actually model bottom up all the subsectors that use energy in order to see what will happen in future. And once you do that, then you will see that in Europe, in most of countries after 2020, there is no more growth in energy demand. And this is one error that I found in many energy planning studies, that they project the energy growth together with GDP forever. It doesn't happen, because it doesn't have to happen. Another side is when you think about energy supply modeling. If you are considering variable renewables, you have to do at least 8,760 time series analysis. Otherwise, you're not going to get good results. And if you are modeling only power system, you will not get any useful results at all, because the future is integration of power, heat, transport, water, and all these sectors. You have to model them together. Otherwise, your solution is that there is no solution, which is an answer we have heard many times before. But if you want to do the right energy planning, you have to integrate all these sectors together. Coming back to the prices, there was a gentleman from Serbia that was saying that renewables are expensive, solar is expensive. That's not exactly the truth. If you look at the price of PV in the last, between 2008 and 2012, the levelized cost of electricity has fallen 4 or 5 times. The last tender for PV in Abu Dhabi is at 21 euros per megawatt hour. It's absolutely the cheapest energy already. If you look at the last auction in Germany at 72 euros per megawatt hour, and then extrapolate that to Balkan area which has higher insulation, we should be getting around 50 euros per megawatt hour now for 10 megawatt project. For a 100 megawatt project like this Abu Dhabi, it should probably be around 40 euros per megawatt hour. So we are approaching era when solar will be absolutely the cheapest energy. If you compare other technologies based on levelized cost of electricity and on their market position, this is important. You cannot calculate LCOE based on 8,000 hours per year. There will be no more power plants working 8,000 hours per year, because in market situation you have to make your space in the market. So if you're building a coal power plant, you can expect at most 4,000 hours per year. And then your coal power plant is, of course, more expensive. So if we compare the big power plants, we find out that wind is actually now cheaper than coal. Renewables are cheaper than fossil fuels. But the problem is how to integrate them. We have seen last 15 years that in European Union, two major new renewable technologies have been actually invested in, wind and solar. So it's actually what I was saying before, it's the result of the transition. Gas is the only fossil fuel in which there were investments. The old technologies are being slowly phased out, but as we have seen, the phase out is much too slower because, of course, there are strong interest in old technologies like coal and nuclear. When we look at the share of renewables, Paul said Denmark is #1, yes, but there are also some interesting countries like Ireland, Poland, Cape Verde. In Africa, I did the energy plant there some 15 years ago. Spain, Uruguay, which has crossed over the 20% integration limit. And that's what is easy to integrate. Everything else under 20% limit, it's actually quite easy. If you go above this, then you have a problem how to do it. You have to think about technologies how to integrate so much wind. If we look at solar, some countries are already at 8%. It's easy to integrate around 10% of solar. Above that, you need to think about technologies for integration. So what do? We need more grid capacity because it's much easier to integrate if you have everything connected. Southeast Europe, I will talk about it later, but it's very well connected, so this is not a major issue in Southeast Europe. We need to do flexible thermal power plants. We have thermal power plants, but we have to make them flexible so they can respond quickly to the market needs. They can do that. This is not a technical problem. I'm a mechanical engineer. If you tell me that it's not possible, pay me and I will make it possible. It's very simple. The third important thing is that we need power exchanges, because on power exchanges we get the transparent price of electricity. And then we can easily remove the feed-in tariffs and get the right balance of different energies. And we have to couple those power exchanges. The next step is to build demand response by integrating power, heat, cooling, transport, water systems into what Henrik Lund is calling smart energy systems. And only in the end, we need energy storage. So energy storage is the last defense. We can think about it when we have solved all of this. And we will see later how well we can do without energy storage. So when we talk about coupling of power markets, we have done already quite a lot. On the European scale. All the green countries are already coupled, and they have a price which is the most transparent and cheapest possible according to the balances of the production capacity that is available. The light green one is coupled among themselves. After 2018, it will be coupled together in one big European system. And now we have to work on the Southeast Europe, which is not yet coupled, but at least some countries have markets. Then there is an issue of balancing. They say, well, this is very expensive. We need more tertiary reserve. This is not true. We don't need it. If you look at Germany solution for the tertiary reserve, it's actually extremely cheap. You just built 15 minutes intraday market and you solved your tertiary reserve problem, because there is a huge excess of power already installed in Europe. And it will be even more excess because we will have decreased consumption of energy in the future. So we can solve the integration problem up to 15 minutes level. The lower level, it's a minor issue. What happens as consequences of market liberalization is that we can forget about baseload. Baseload is technology of past. You cannot actually pay for it on free markets because we need flexible power and not baseload. There is importance of balancing power. So for transition period, we will need gas and hydro. Old coal power plants can work for some time, cycling, up to 4,000 hours by 2020. By 2030, that means 2,000 hours. That's not enough to build new ones. But if you can retrofit the old ones in order that they can respond to wind and solar, then they can stay working for some time. And we need, as I said, demand response, which may be technologies like power to heat, power to water, e-mobility, power to synthetic fuels or e-fuels. How it works in Denmark already. Power to heat technology. This is a small district heating plant in Skagen. When electricity is expensive, like in those hours, then CHP is working and producing electricity and heat and selling it in the market. When electricity is cheap, like here, or even negative price, then they buy electricity and convert it into heat with electric boilers. Heat pumps are even better. They're more efficient, but electric boilers are much cheaper. And electric boilers are actually have payback of few hundred hours per year, while heat pumps need to have 4,000 hours per year. Then we come to the next big step that is just starting, thanks to Elon Musk and Tesla and all this process of moving cars to electrical powertrains. Last year, 550,000 plugged-in hybrids and battery cars were sold in the world, and this number is doubling every year. If we look at electric cars, they are actually reducing consumption of energy for primary energy for 80%, for 5 times, if they are run on a renewable electricity. So this is a major energy efficiency solution for our energy scarcity problem. But it also can give us an interesting help for renewables in power system. If you look at this following situation, let's say Austria, everybody has electric car. Everybody arrives home at 5 o'clock afternoon. Everybody plugs in its electric car into a fast charger. Everybody will want to have fast charger at home according to JRC. That means 290 gigawatt demand in a system which has only 14 gigawatt installed for half an hour. After that, all the cars are full, no need for it. Why not using this immense capacity in order to balance the power system? So we did a simulation of Dubrovnik area to see how much we could use electrical cars to balance excess wind. And it's a very small amount of energy that you actually need to power all your cars. It's 5 to 10% increase on your electricity demand, but it's huge power. So you can actually use it in order to balance the power system when there is excess of wind. And with these two technologies only, we can actually do miracles. If you look at integration of wind power, without flexibilities of the system, demand response, then, and if we say that we can easily lose 5% of potential production, because that will not decrease the economics of the project, we can go up to 20% of wind penetration, not above that. But if we add power to heat technologies and link it to district heating, and there is a lot of district heating in Eastern Europe, in some countries more than 50%, then we can easily go to 40% wind penetration. If we add electrical cars to that, we can go to 80% penetration. And this is cheap, because district heating is anyway something that we have. Power to heat doesn't cost anything. Electric cars are coming anyway, and batteries from electrical cars are not going to be paid by the power system. They will be paid by the transport system. We don't like these power walls, because power walls are actually subsidizing coal. They're protecting coal against market solutions. Transition is much better than everything is solved on the network level. It's the cheapest and fastest transition. What then? We still have 20%, we cannot solve that easily. Transport, like road freight, shipping, aviation, cannot be easily electrified because we don't have batteries of high energy density. So we need to find some energy for them. That makes around 20% of demand, which we cannot electrify. Also, some industrial processes cannot be electrified. If we use biomass, on a global level, we can basically cover half of that by biomass. If we use more biomass, then we are not sustainable. In Southeast Europe, we can go further than that because Southeast Europe is rich in biomass. But still, we will need a part of energy which we don't have a cheap way how to produce. Synthetic fuels made of electricity, CO2 and H2O are a solution to that. But this is not a cheap solution. So when you start from this point, this is not cheap anymore. So up to 90% renewable energy system, we can go very cheaply without any problems in the next 20 years. From 90 to 100%, we don't have solutions yet. If we look at example of the model that we did for Southeast Europe, 100% renewable Southeast Europe, you can download it from this paper in Applied Energy. You can see it's a lot of renewables, lot of heat pumps, solar thermal energy storage. We need it for seasonal storage, some geothermal, lots of hydro, closing down nuclear power plants, and a reduction of significant reduction of thermal power plants. And we come to the following comparison between 2012 and 2050. There is a huge decrease of primary energy supply. Why? Buildings are more insulated. They're using mostly waste heat from plants or renewables. Also, cars are electrified, so they use 1/5 of energy. And power system is much more efficient because renewables are more efficient than the Rankine cycle. You lose 2/3 of energy in the power plant. And it's based on renewables. It's quite a lot of biomass because Southeast Europe has biomass. So for us, it's even easier to do the energy transition than to the rest of the world. As you can see, it's quite a lot of PV, and wind makes more than half of electricity mix in the power system. And how it looks during the daytime, one winter day, which has more demand, and which has some solar, not so bad, and then quite a lot of wind, and the summer day with more solar but less wind. In the end, to conclude, wind and solar are coming because they are now cheap. You don't need to subsidize them heavily anymore. You still need to subsidize them up to a point in order to move them through the barriers, because the barriers are huge. Fossil fuels are hugely subsidized. There are huge lobbies of miners in Europe protecting their jobs, which is completely understandable. We have to find new jobs for those miners. Why not moving them to PV businesses, like Slovenians did in Velenje, for example? It's nice. There will be the mission of base loads, which is important for the region. We don't see the future of baseload, and there is still a lot of discussion in the region for building of baseload power plants, but there is no economics for that. Just look at your markets. You cannot really get that price from baseload. There is need to integrate different energy sectors, like power, heating, cooling. Water is very important, and transport systems. And smart energy systems are actually cheap and simple if you do it in the right way. And I also say to my students, it's a great time for engineers. It will be more work for us, not less work for us. So why resist? Thank you very much.